Okay, good. So yes, I'm delighted to be part of this conference. I'm sad not to be in Loughborough with you, but happy to be with you virtually. And so just to set a little bit of broader context in terms of proof assistance, I prefer to use the phrase digital mathematical assistance because proof assistants really can be used for a lot more than proof. But they're now being used to formalize substantial mathematical results, and the technology, at the core, basically is a way of representing mathematical content in a digital way. So it allows you to represent definitions and statements and proofs in such a way that you've got complete detail and very precise semantics and very precise rules of use, to the point where the computer can check the grammar and the rules and make sure that they've been applied to. So there's a sense in which this is brand new. This is it's very new to mathematics. But there's a sense in which it's not new at all. Mathematics has long been about being very rigorous and precise, and this is just a technology that lets you be very rigorous and precise. So it's a technology that lets us that supports what we've been doing all along. So I will, as with this conference, I'll focus on lean in this presentation. I want to emphasize that there are other proof assistants out there, and they're all very good. And a lot of what we're saying here is not specific to lean. And what I want to do is start with a quick lean demonstration. In case, let's see. So in case you haven't seen it before, if this is all new to you, I think it'll be helpful to have something very concrete in mind as to what it means to work with an interactive proof assistant. And for the moment, let's set aside the question of what we're asking students to do or whether this is reasonable. I just want you to give you a flavor for what somebody who's been trained to work with lean, the kinds of things that they do. So here's what's going on in this file. I'm started by telling lean that I'm going to do some basic stuff about the real numbers. So make sure that library is around and available. On line 3, what's going on here is I'm defining what it means for a sequence of real numbers to converge to a real number. So S is a function from the natural numbers to the real numbers, right? Which is just another way of saying that it's a sequence of real numbers. A is a real number. The colon equals says what follows is the definition. And so the definition of the concept is that for every epsilon greater than 0, there is an n such that for every m greater than or equal to n, the absolute value of Sm minus a is less than epsilon. So it's just the definition you're familiar with, sort of written in logical symbolic notation. And if you were teaching this in the class, one of the first theorems you prove for students is that if S converges to A and T converges to B, then S plus T converges to A plus B. So the theorem is named, I've given the name converges to add. S and T are assumed to be sequences of real numbers. A and B are assumed to be real numbers. We're assuming that S converges to A and that T converges to B. And the colon is what the conclusion is supposed to be. So we're claiming that we can show that S plus T converges to A plus B. And lean is smart enough to know that adding sequences or adding functions means adding it pointwise. And lean is smart enough because smart people have introduce the notation and the definition so that that leans that's what lean does. And then so now the colon equals now is supposed to be followed by a proof, and I'm putting the proof between begin and end. So here's where I write the proof. And so here's where I'm typing the proof. And on the right side, lean is telling us where we are in the proof so far. So the way to read the goal on the right side is, at this stage, we've got two sequences, S and T. We've got real numbers A and B. We've got the hypothesis that S converges to A and the hypothesis that T converges to B. And after that turnstile symbol, that's the goal. That's what we're trying to prove. Okay. And so knowing that a converges to statement is of the form, for all epsilon greater than 0, I'm going to start by just you want to assume that, you want to pick an arbitrary epsilon and assume that epsilon is greater than 0. So that's what I just did there. And so now, I have an epsilon and the fact that epsilon is positive. Okay. And then if you think about what the proof is, well, the trick is you're then supposed to, specialize these two values whose, you have to pick a smaller epsilon, like epsilon over 2, so that when you sum them, you still get something that's less than epsilon. Okay. So what we want to do is specialize both of these to epsilon over 2. But to do that, we're going to need the fact that that epsilon is positive. Okay, so let me, oh, sorry, epsilon over 2. Sorry, that's the fact that we need. Okay, and this Lean can do automatically, so we'll let it do that. And so this is a have with the colon, not the colon equal. This is the colon have. And I didn't give a name to this fact, so Lean just gave me the name this, so I can refer to it back as this. But I've just proved that epsilon over 2 is greater than 0, and so now I can use it in the rest of the proof. Okay. And so now what we want to do is we want to specialize this assumption to epsilon over 2. Okay, so I'm just do cases HA at, let me put parentheses around it, epsilon over 2, and this. Okay. And what that did roughly is, the statement that should give us an N and an M for that particular data. And let me just, Lean just chose arbitrary names. Let me just give them. So I'm going to use, case this with. Let me use the name NA for the N that's associated to, the A value. And let me use HNA for that assumption. Okay. So at this stage, from this, I've gotten a value, a natural number NA. And I have the fact that for all m greater than or equal to NA, the absolute value of Sm minus A is less than epsilon over 2. And similarly, we want to do this for the other sequence. Right, so good way to do that is to just cut and paste. And so that was the B1. Yeah, okay. And so my list of data and hypotheses are growing, but I have an NA, and for everything m greater than or equal to NA, the absolute value is small. And we have an NB, and for every m greater than or equal to NB, the absolute value is small. So now I want to choose the N for the conclusion. And so what value of N do I want to choose?
Max.
Yeah, the max. Did I hear max? Was that the? Yeah, you want something bigger than NA and NB, and so the maximum will do it. So I can tell Lean to prove that existential statement, use the maximum of NA and NB. Oh wait, what am I doing wrong?
NB.
Oh, NB. Good. There we go. Yeah. What was the error message? I mean, this is part of the fail to instantiate goal with blah blah. You get an error message and a squiggly line. And yeah, good. So that fixes it. Okay. And so now, in the interest of time, I'll do what they do on the cooking shows, where they kind of bring out something that's already been pre-chopped a little bit. We want to then basically apply this thing. So since M is bigger than the maximum, it's bigger than NA, so we should be able to get this. And yeah, so let me just cut and paste a couple of lines that will magically do that for us. No. Oh, sorry. At this stage, sorry. Before I do that, I want to prove a universal statement. So I want to say let M be arbitrary and assume that. Yeah. So let me do that. Intros M, and I don't know HM. Is that what I called it? Or M greater than equal. So that's what I called it. Okay. And now we specialize that. So now we have all the data before that, and now we're just down to a calculation. Given that, so I put the cursor here. Yeah. Given that Sm minus A is less than epsilon over 2, and given that Tm minus B, the absolute value is less than epsilon over 2, we want to do that calculation. And again, as on the cooking shows, when they just kind of pull out something out of the oven, let me just cut and paste the calculation. So there it is. So the absolute value of S plus Tm minus A plus B is, just rearranging terms, is the absolute value of Sm minus A plus Tm minus B. Right, so abel is just an abelian, works in any abelian group. It just does the calculation. Now we use the triangle inequality. So the absolute value of the sum is less than the sum of the absolute values. And in Lean, that's sensibly called, apps add. And then since, this one is less than epsilon of 2 and that one's less than epsilon 2, the sum is less than the sum. So that's add less than add. And finally, those two things are equal to epsilon. Oh, and I forgot the justification. So let me put it in. This is actually the norm num tactic that Mario wrote for Kevin a long time ago, and we use it all the time. So it can calculate that epsilon over 2 plus epsilon over 2 is equal to epsilon. Okay, and that's it. That's a Lean proof. So that went by quickly. I mean, I don't expect that, that if you've never seen it before, I don't expect that you got all that much out of it, but hopefully at least a flavor of what the business is about. Okay, so back to the slides. Yeah, so formal methods and proof assistants like this are they are playing an important role in computer science and engineering for verification purposes. So verifying hardware, software, cyber physical systems, financial technology. So there's an industry where these things are used. And so what's most notable in recent years is that the technology is now being increasingly be used for mathematics as well. And it does a lot of things. In addition to verifying proofs, I mean, sometimes even just having precise statements of mathematical results and definitions and theorems is important. So it lets you do that, but it also lets you prove them and verify that your proofs are correct. By having precise statements, it facilitates collaboration. You can work collaboratively with people, and there's no ambiguity about what you mean. There are now, grand mathematical libraries that, that users can kind of explore and search, and find mathematical results there. You can use the technology as front ends to, numerical and symbolic computation. There's the possibility of using digitized mathematics for, automated reasoning, machine learning, and, other methods of discovery of mathematics. And so, teaching is yet just another possible, potential use of the tools. Right. And so even if we just focus on teaching, I mean, the tools can also and are being very much used to teach aspect of logic and computer science as well. So again, it's notable that this conference is focusing specifically on teaching mathematics. So I will do the same. And so the question is, well, why might it be a good idea to use Lean to teach mathematics? And the students, especially James, I think, mentioned the first of these, which I think is really the most important aspect. The current model right now is that, you give students an assignment and they go home and they work on it and they don't know whether it's right or not and so on. And they write something down and they hope for the best and they turn it in and it comes back from the grader, all marked up a week later. And, by then they've moved on and they look and they see this where the points were taken off and where the red marks are and they glance at it and put it in a bag and then never look at it again. I'm not an educational researcher, but I do know that the data is that immediate feedback is really important. Just having error correction, having students know what they do wrong and correcting it quickly is very important. And this with when you're working with Lean, it's immediate. When you're right, it's right. When it's wrong, it's wrong right away. But also, I mean, it can be frustrating, but it can also be a lot of fun. I mean, working with Lean is this constant cycle of being challenged to do something, and then you're frustrated, and then you get it, and then you're really happy, and then there's the next step, and then you're frustrated again, and then then you get it. And so there are all these kind of steps and small victories, and it feels really good. It's like playing a game. It's like you against the computer, and God damn it, I'm not going to let that computer win. And so it really, can get students engaged when you're trying to beat the computer, and students will just keep at it, for as long as it takes. The technology, I've argued that the technology will be important for mathematics. And so, if you're teaching students to do mathematics, well, if you believe that the technology will be important, then teaching them the technology is part of teaching them mathematics. And it's already being used for other things, as I said, in computer science and industry. So, we have to recognize that a lot of our mathematics students are going to go off to programming jobs and so on. And knowing some formal methods could well be helpful to them. So yeah, downside, again, students went over a lot of them, did a good job, James, especially these. So first of all, proof assistants are hard to use. They're not designed for teaching. They're designed for industrial research and academic research and industrial use. And also, they can be very, very much a distraction to the mathematics. I mean, all the names of the theorems and the tactics and so on. That's not mathematics proper, right? That's stuff on the side that's specific to the, the names that the library designers chose and so on. And so that can be a distraction from mathematics. And the students also gave us some good strategies to mitigate that. So I think you have to choose the tasks for students very carefully, and make sure that they have all the information in front of them that they'll need to succeed at the task. We want to set up students to succeed, not set them up to fail. So we have to make sure that we're giving them a context where they have everything they need to be able to do what we ask them to do. And the fact that proof assistants aren't designed for teaching, well, they're being adapted for teaching, and the design is ongoing. So I think there are, well, things that can be done for provers in general and are being done for provers in general, and especially in the education setting. So I think there are ways that we can use automation and better interfaces to really help students focus on the mathematics and downplay the distractions. And I'll come back to that in a little bit. Okay. So questions as to how we can incorporate Lean in the classroom. Well, there are lots of ways you can imagine doing it, but let me mention just kind of 3 models. So one is that, so if you're teaching an introduction to mathematics, use Lean, right? So, lots and lots of universities have a standard introductory course to mathematical concepts and proof. It's the course that does, Kevin mentioned it, sets, relations, functions, proof by induction, a little bit of number theory, divisibility and so on, maybe a definition of the real numbers and convergence or something like that, maybe a little bit of algebra, maybe a little bit of discrete math, probability, but, something that's basically supposed to introduce students to how to think about mathematical concepts, how to speak mathematics, and how to write, proofs, right? So you can try to use Lean in that setting. The problem is a lot of those courses are already kind of jam-packed with stuff, right? And they've been, people have been teaching them for a long time, and they have their curricula, and they're trying to squeeze in. So there really isn't room, right? So another possibility is to say, well, forget about that. Let's just let them learn their introductory mathematics anyway, just the old-fashioned way, right? The way that we used to. But then, give them, once they know a little bit of mathematics, then come back and then just teach them, give them a course that's specifically about using Lean or another proof assistant, and specifically about formalizing mathematics. Don't conflate the mathematics with the formalization, 2 separate topics. Learn the mathematics and then learn how to formalize. And then, of course, you can, let's see, Lean as either, so you can use Lean as either an optional or required add-on to a conventional course. So ideally, once you get going, it would be great to be able to use Lean in any mathematics course, just to kind of reason and explore concepts and, give students exercises where they can get immediate feedback. This presupposes that, it's too much to ask that, anybody who wants to use Lean in the course spends the first 3 weeks giving students an introduction to Lean. So it kind of really, for the third one to work, it's much better if there's kind of some standard way for students to get the requisite background in Lean to avoid duplication. So I'll focus on the first 2 models, right? And so let me kind of summarize them there, right? So model 1 is you use Lean in an introduction to mathematics, and the other one is you use Lean in an introduction specifically to formalization and interactive theorem proving. Right? And I just want to emphasize that these are just 2 different things, right? So the audience is, so if it's introduction to mathematics, you don't have to assume students know mathematics. The goal is to teach them mathematics. Whereas, when you teach them interactive theorem proving, you can assume that they already know some. The introduction to mathematics may be for everybody, even non-mathematical majors. Whereas when it comes to formalization, that might be, so first of all, specifically for students with mathematical background, maybe even specifically for math majors, and maybe it's even optional. So it's only for the math majors who are particularly want to do formalization. And so, the goal of the first is to teach mathematics simpliciter, and the goal of the second is to, specifically to teach formalization. And it seems that the second is really an easier sell, right? It's easier, if you're teaching a course on interactive theorem proving, students are not going to complain, well, why do I have to use a proof assistant? Well, that's what the course is, right? You don't have to take it. And, if you think that formalization is an interesting, a worthwhile thing for students to learn in its own right, then you don't have to justify, then teaching formalization, teaching students to use proof assistants is a good thing. It's what the goal is. Whereas, you have to make a much, it's harder to make the case that formal methods are good for mathematics, overall. And so, there I think is where we really need the educational research more to justify it. Okay. So so I already know here are some of the courses I know about. So you've heard from Kevin and you've heard from Gihan. There are other very good people teaching very good courses and using Lean that you should know about. So Heather Macbeth, Patrick Massot, Sina Hasratpour, and Matt Ballard. By the way, I should have mentioned these slides are already online on my webpage, and everything in red is a clickable link, so you can go find it online. and and follow up and get more information about what these other instructors are doing. Interestingly, only Kevin is specifically targeting a formalization course. So all of these, I think, are really more as using Lean as add-ons or to, well, I guess Patrick is somewhere in the middle. As Kevin mentioned, first he teaches, first they teach a course in analysis, and then maybe the second term is more specifically on formalization. Okay, but so you have kind of both kinds. So in the time, so in 10 minutes I have left, so let me just talk about two teaching efforts, two things that I've worked on along these lines. So the first is the course that Gihan mentioned, Logic and Proof. So there's an online textbook that I'll show you in a second that was written with Rob Lewis and Floris Van Doorn. And that's on the Model 1 side. So I use this in an introduction to Logic and Proof at Carnegie Mellon. It was targeted to freshmen and sophomores from a variety of backgrounds. I had students from modern languages and business majors and so on. So there was no assumptions, prerequisites, beyond high school mathematics. And the goal of the course was to be an introduction to symbolic logic, an introduction to mathematics and mathematical reasoning and proof, and formalization, in service of both of those. And the other one, which I'll tell you about briefly, is an online textbook, and tutorial that I'm working on jointly with Kevin and Rob Lewis and Patrick Masseau. And that is specifically, this is really Model 2. The goal of this is just to teach people who know some mathematics as quickly as possible how to formalize mathematics. Okay, so let me say a little bit about both. So Logic and Proof, the stated goals of the course were to teach students how to write ordinary pen and paper, readable, literate mathematical proofs. Also teach them symbolic logic and how to write statements in symbolic logic and prove things in a formal proof system and so on. And then Lean was used not, as an artifact of interest in its own right, but as a way of helping students understand logic and as a way of helping students understand mathematics. And I think the next slide is basically a summary of the contents. Yeah, but let me just do it this way. Let's see. So yeah, there it is. So here's the textbook. You can find it online at leanprover.github.io, Logic. And if you search for it or go to my webpage, you can find it. But it's, the first maybe third, maybe a little bit less than third of the course is specifically logic. So we did propositional logic and natural deduction. So this is what you get in an intro logic class. And then a chapter, here's how you do it in Lean, propositional logic and Lean. Then some classical reasoning, proof by contradiction, and semantics, truth table semantics, then first order logic and how to say things in first order logic, natural deduction. And then, here's how you do it in Lean. Okay, and a little bit of model theory, the notion of what it means for a formula to be true or false in a model. And then here's your intro to mathematics. There's, sets, relations, functions, natural numbers and induction. So, right. And that was really designed to be looked as just kind of a standard sets function, relations function as, standard and routine as you might, you would expect anywhere else. But then the novelty is that, every other chapter, so sets, and by the way, here's how you do it in Lean, and relations, and here's how you do it in Lean, and functions, and here's how you do it in Lean, and then natural numbers and induction, and here's how you do it in Lean. And then beyond that, the Lean kind of falls away, and then it's just, there's a little bit of number theory, combinatorics, real numbers, the infinite. And then finally tying it together at the end, there's a little chapter on axiomatic foundations that kind of brings together the mathematics and the infinite and so on. So the course we go at a good clip. We covered a lot of material, but it was always very enjoyable to teach. Okay, coming back here. Right, so just for an example of how we use Lean. So, in the informal mathematics part, I mean, this is something that we ask students to do. We teach them what it means for a function to be injective, and we ask them to show, so here's a homework exercise. So let f be a function from x to y, g from y to z. Show that if g composed with f is injective, then f is injective. And then there's another one where you Let's see. Oh, but in fact, you can have G composed with F injective, but G not injective. So give a counterexample to the other way around. But here's a student answer to the first one. It's a pretty good proof. It's not perfect, but it's if your students write this, you're pretty happy. We tell them not to use arrows, symbolic notation when they're writing mathematical proofs. They should use language. But suppose G composed with F is injective, then by definition for all A and B, the definition of what it means to be injective. Oops, sorry, what happened? Here's a common student mistake. At this point, they want to say let X and Y be arbitrary elements of X, and suppose F of X is equal to F of Y. And, students do this a lot. They say instead, now assume that there exists some X and Y in X, which is kind of a funny, we know what they mean, but it's not how they should be phrasing things. But they're pretty much getting it. But the point is that you can do exactly the same thing in lean. Let x1 and x2 be elements of A. Suppose f of x1 is equal to f of x2. Then g of f of x1 is equal to g of f of x2, just by using the previous fact. And then x1 is equal to x2 by injectivity. Okay, so they can also do, and this is also a student exercise and something that they're expected to do in lean. And there's a corresponding one for surjective functions. Okay. So for teaching that class, we want to make it clear that there are three distinct languages. They're teaching them mathematics on the one hand, symbolic logic on the one hand, on the other, and then, on the third hand, you're teaching them formal proof. But students are pretty good about that. They don't get the different languages confused, and somehow doing them all in parallel, it's kind of synergistic. It seems to be synergistic, right? They can see exists elimination done formally. They can also see it happening informally in mathematics, and they seem to be able to connect the two. And they like the course. The course is always rated highly. It goes over well. Students seem to enjoy it. Okay, so I'm running low on time. Let me mention that specific features of the course that you might decide not to adhere to is that the course does have this explicit emphasis on symbolic logic, and you could do away with that. You can just say, look, I want to focus on mathematics. And the other thing is that the way of writing proofs is more of a declarative style than a tactic style, and I think that there are pluses and minuses, but you could reasonably not do that. Let's see. Let me mention one other thing. So this summer, we're going to, at the Hoskinson Center, we're going to start trying a different approach. So there are actually three versions of a Concepts of Mathematics class at Carnegie Mellon. So there's one kind of introductory one, there's one for math majors, and there's one for computer science majors. And I don't know the exact numbers, but taken together, I think they've over 1,000 students. And we're going to try to work on an informal proof or a semi-formal proof checker for this class. And the rules we've set ourselves is that these courses exist. They've been taught for a number of years. They're a team of instructors. They've got their teaching materials. We're not going to change the materials dramatically or the curriculum dramatically. People have been dickering over the curriculum. We're going to figure out how to work with the existing course material. But we're going to try to find a way to design a proof checker that they can use. So you can, for example, give students exercise. We say, well, write an informal pen and paper proof of this fact, but also write a formal one and have it checked right away and get feedback right away. And the game is, we think it's okay to give them formal syntax for statements, like tell them you have to write continuous F, when you mean F is continuous. We can give them a regimented proof language. You have, commands like you can say have, you can say show, you can say assume, and so on. But the justification should be something like, well, just use this follows from lines 3 and 5 in the definition of continuity, right? You shouldn't have to be naming tactics and arcane theorems. Maybe a big theorem like the mean value theorem or something like that, but no, crazy theorem names or anything like that. And so we're going to start experimenting to determine the extent to which conventional automation can do that. Okay, so I'm running out of time. Let me just mention the Model 2 thing that Kevin and Rob and Patrick and I are working on. So we're working on a tutorial called Mathematics in Lean that is specifically designed to teach people who know some mathematics, again, to formalize as quickly as possible. Let me just kind of flash it up on you there. So it's meant to be read online, side by side. You're reading the text and you've got Lean, right next to you when you're working through the exercises. Well, there it is. So it kind of recapitulates what you do in the introduction to math class. So basic reasoning and some logic and sets and functions and some number theory and some abstract algebra. And it's still in progress, so we're still going. But the idea is to, so now you do it formally. Okay. And so quickly, the design decisions are, don't worry about theory, logic, foundations, syntax of lean specifically, but just focus very much on examples. Right? Start with basic skills, calculation. Here are some examples, and here's how to do it, and then you try it. And the style is, here are some examples, now you do something, try it out. And then here's some more examples, here's some more skills, and then try it out. And so that's, it's work in progress, but I think it's coming along nicely. And I plan to use that in another introductory course at Carnegie Mellon in the fall. And so we'll see how that goes. So, okay. So conclusions. Yeah. So I've made the case that formal methods are, bringing about a digital revolution in mathematics. I think, in the years to come, they will have an effect on the way we do mathematics. But even setting that aside, I think specifically for pedagogy, there's a lot of potential.